We propose an emotion-aware social navigation for bipedal robots with deep reinforcement learning. This figure illustrates the whole framework of our approaches. Firstly, we obtain human facial emotions, including three types: neutral, happy, and negative. Furthermore, we collect raw LiDAR scans that detect surrounding objects, including static obstacles and dynamic pedestrians. Next, we convert the emotions and LiDAR scans into sequential LiDAR grid maps, showing collision areas, discomfort zones, and spatiotemporal dynamics of evolving environments. Subsequently, we extract latent features with an encoder to reduce the state space of deep reinforcement learning. The encoder is composed of convolutional neural networks. Successively, we combine the latent features, goal positions, and robot states, and directly project them into the robot actions through an actor-critic deep reinforcement learning pipeline. The actions include heading angle and sagittal speed, which are regulated from the reduced order model of bipedal robots. Finally, we leverage a planner to obtain foot placements, and a full-body controller to generate joint-level commands. We directly train our policy with the full-body bipedal robot, which can reduce the dynamics gaps for the motion planner, only relying on reduced order models. Initially, we train and test our navigation policy in a physics-based simulator, using a full-body bipedal robot and a full-order dynamics. Firstly, we compare with other baselines. DRL-VO finally failed due to collisions. The torso-yaw angle of DWA is vibrating. The navigation of single LGM is slow because it only uses a single grid map. Next, we deploy our policy into a more complex simulation scenario, illustrating that our navigation policy enables the bipedal robot to adapt to complex and interactive scenarios integrated with pedestrian emotions. Then, we transfer our simulated navigation policy into real-world scenarios with diverse pedestrian motion patterns. The robot should avoid static obstacles while interacting with pedestrians. We include several representative motion patterns. For example, pedestrians cross in front of the robot, walk, and suddenly stop in front of the robot, group together to cross in front of the robot, and randomly interact with the robot and other pedestrians. Furthermore, we randomly set pedestrian emotions. Accordingly, our social navigation policy can well adapt to its own behaviors to avoid collisions and reduce intrusions into discomfort zones of pedestrians, indicating the potential of sim-to-real transfer of our navigation policy. In addition, we integrate robot localization, pedestrian detection, and emotion recognition into our pipeline to further validate the practicality of our emotion-aware social navigation. These modules are achieved by an onboard stereo camera and corresponding SLAM and perception algorithms. Pedestrian states can change between static and moving, and their emotions also alter between happy, neutral, and negative. To investigate further, we increase the environment complexities. For example, pedestrians group together and keep static to block the robot. Moreover, we increase the pedestrian density to make the scenario more crowded. Even under these time-varying and highly dynamic situations, our robot can still avoid collisions and reduce intrusions into discomfort zones, further demonstrating the sim-to-real transferability of our integrated navigation policy in pedestrian-rich environments. Finally, we deploy our navigational policy into more realistic environments, like the campus after classes. Pedestrians are more crowded, and interactions are more complicated. The bipedal robot can still achieve the emotion-aware social navigation task.